Hello everyone, welcome to my video on uniform motion. So this is first year physics, which I'll show you on how to solve problems involving uniformly accelerated motion. So these are the notes, and this content in this video is mostly suitable for first years, where we'll talk about uniform motion in a straight line and motion in 2 dimension. We'll also look at objects which are moving. Of course, we'll also look at graphical representation of motion. All right, so let's start and get into it. So we'll start with speed. So let's just see what we have here. Okay, yes, yeah, this is uniformly accelerated motion. So start with speed. So speed is just a scalar quantity, and that's something which we know. Speed is a scalar quantity, meaning that it only has magnitude, and the direction is not included in speed. So if a distance L is traveled by an object in time t, then average speed is equal to total distance over time taken. So that is our equation 1, and this is something which we all know, or which most of you know. Average speed is just distance over time taken. Okay, so for now we'll just be looking at definitions, then from there we'll start looking at problems. So velocity is a vector quantity, and if an object experiences a vector displacement of size s, so displacement is mostly represented by the letter s, during a period of time t, then average velocity is equal to vector displacement over time taken. Yeah, that is how you solve for average velocity, vector displacement over time taken. So that is in equation form, you can write it as v average is equal to s over t. So that can be your equation 2. Now you should note that displacement is just the distance covered by an object in a given direction. And let's look at something here. Let's look at the difference between now displacement and distance, because some students get confused between the difference between displacement and distance. Let's just go down here where I wrote the difference. Okay, so the difference between displacement and distance, or between distance and displacement, is here. So we're saying that displacement, or rather let's say distance, is the complete length of the path between any 2 points. That is called distance. Okay, the complete path between any 2 points is distance. How about displacement? Displacement is the direct length between any 2 points. Okay, so in this case we have point A and B. So now displacement is the direct length between any 2 points when measured along the minimum path between them. Or in other words, you can say displacement is just the shortest path between 2 points. So when you look at point A and point B, to get to point, for someone, let's say this is a person at point A and this is a person at point B. For the person at point A to get to point B, they have to use this curved path here, this curve. They have to go all the way. Now going all this way is called the distance. So this person is covering this distance all the way, and then until they get to point B. So that's the distance covered. This length of this path is the distance. But when you look at the shortest path between A and B, is just this straight line going all the way that side to B. So this straight line represents the displacement, which is the shortest path between 2 points. And as you can see, it's in a given direction. It's from A to B. So that's displacement. The shortest path between 2 points in a given direction. That is displacement. Alright, let's go back to our notes. We continue with what we're talking about. So here we're saying that the displacement vectors and velocity vectors directions are the same. Of course, the displacement and the velocity should be pointing in the same direction, because wherever you go, that's where you cover the distance, right? That's where you cover that displacement. Okay, wherever your motion is will be also your displacement covered. Now, the measurement of velocity and speed is done in units of distance divided by time, such as meters per second or kilometers per hour. And acceleration, here, measurement of acceleration is just the rate of change of velocity over time. That is acceleration, the rate of change of velocity over time. And average acceleration is equal to change in velocity vector over time taken. That is how we measure the average acceleration, change in velocity over time taken, which is just A average is equal to final velocity. This is V subscript F represents the final velocity minus the initial velocity over the difference in time. Okay, so this is T subscript F is T final minus T initial here, as in equation 3 shown there. So where T is the amount of time that the change took place here in this equation, and Vi is the initial velocity, this V subscript I is the initial velocity, V subscript F is the final velocity here. Okay, now velocity divided by time is used to calculate acceleration units. Okay, yes, that's true. And units for acceleration can therefore be meters per second or meters per second squared. I know you're used to the meters per second squared. It's the same thing as this. So instead of writing this, you can write meters per second squared as I showed you in class. Now, you should also be aware that acceleration is a vector quantity. Acceleration, yes, is a vector quantity because it has a direction. It points somewhere. Alright, moving on to uniformly accelerated motion along a straight line. So we're looking at uniform motion along a straight line. What do we mean? We mean uniform motion in one dimension. A straight line is one dimension. So if instead of saying accelerated motion in a straight line, you can even say uniformly accelerated motion in one dimension. Alright, so that's what we'll focus mostly on. So this is a part where we'll look at the equations of motion in one dimensional motion. We'll look at those equations of uniform motion. Now, in this case, the acceleration vector is constant. Okay, that is why it is called uniform motion. Uniformly accelerated motion is because the acceleration is always maintained constant. Okay, if we replace A subscript V by A, okay, so now, okay, yeah, this part is just derivation of uniform motion equations. So this part going down here, it's showing the derivation of the equations of uniform motion. So all this part is showing us how to derive those equations of motions, you know, the fancy equations of motion. Okay, so you can check out the derivations on your own. Otherwise, we'll just continue from the equations of linear motion. So the equations of linear motion are these in this square. These are the equations of uniform motion. Okay, and for these equations, they are all for constant acceleration. So this equation is V F is equal to Vi plus AT, a very common equation which you probably did in the 12th grade. Average velocity, which is just Vi plus Vf over 2, of course, for constant acceleration. And x final is equal to Vit plus half AT squared. So this is another equation relating position as a function of time. So it relates position, which is x final, as a function of this time here. Okay, the first one is just relating velocity as a function of time. This one is just relating position as a function of time. And here we have velocity as a function of position, which is v subscript f squared is equal to vi squared plus 2a x final. Okay, so these are the so-called equations of uniform motion, and these equations of motion have been written here assuming that the object is moving, or let's say the assumption was that an object moving along the x-axis. These equations of motion were derived assuming the object is moving along the x-axis. That's why you see displacement represented with letter x here. So the assumption was that motion is along the x-axis for these equations. Now, these equations of motion are used to solve any problem involving a particle under constant acceleration in one dimension. So back again to one dimension. One dimension meaning in a straight line. That's what we mean. One dimension meaning that it's either in the x-axis alone, or either in the y-axis alone, or either in the z-axis. So that's what we mean by one dimension. Okay. Now, when evaluating motion along a straight line, direction is crucial or important, and one must choose a positive direction. So you must choose a positive direction when you're working out these problems. Okay, you must choose which direction will be positive and which one will be negative. So either course of action could be seen as advantageous, yeah, and a displacement or velocity or acceleration must be interpreted as negative if it is going the wrong way. So a displacement, velocity, or acceleration must be interpreted as negative if it is going the wrong way. What do we mean? What we mean here is that if it is going opposite what you've chosen as positive direction, if it is going to the other side from what you've chosen, then it has to be interpreted as negative. Alright, let's look at an example quickly involving uniform motion. So in most of our problems, we'll be working out using these equations of uniform motion. Okay. Alright, let's look at example 1 here, talking about a jet. So we have a jet that lands on an aircraft at a speed of 140 miles per hour. So this jet is landing on an aircraft at a speed of 140 miles per hour, which is just 63 meters per second. Part A is just saying what is its acceleration, assumed constant. So this acceleration of this jet is constant, meaning that we're going to work out our problems using equations of uniform motion. So what is its acceleration if it stops in 2 seconds? So this jet lands on an aircraft. Okay, so now the question part A is saying is what is its acceleration if it stops in 2 seconds due to an arresting cable that snags the jet and brings it to a stop. Okay, so that's part A. Let's look at part B. If the jet touches down at x subscript I equals 0, what is its final position? What is its final position? Alright, so let's start with A. What is its acceleration if it stops in 2.0 seconds? 2.0 seconds due to an arresting cable. Okay. When you look at this question, the first thing one wants to do for part A is assume that this jet touched down at the origin. Let's say that the point at which it touched down is the origin, and of course it was moving with an initial velocity of 63 meters per second. So I want you to imagine a jet which is flying in the air and then it is landing on an aircraft, right? It is landing on some aircraft. but the speed at which it is landing is of course 63 meters per second. But when you look at the question, it's saying that this jet comes to a stop, meaning that if it stops, its final velocity will be 0. Okay, so the question now is, what is its acceleration? So we'll use an equation which involves final velocity, initial velocity, and because from the question we have the initial velocity and we have the final velocity, which is 0 because it stops, and we also have the time in the question. We've been given the time. We want to know the acceleration. So from the equations of motion, we can choose an equation to use. If we look at this equation, it has the final velocity, initial velocity, the time, and the acceleration part. So automatically we'll go for this equation because it has all that we need to work out the problem. So we'll use this equation of uniform motion. Alright, so let's use this equation here of uniform motion. So which is this? Vf is equal to Vi plus At. So you can make A the subject of the formula by saying A is equal to Vf minus Vi over T. Okay, we know Vf what it represents, Vi what it represents. So Vf is the final velocity, Vi is the initial velocity. Hence A is equal to 0 as the final velocity minus 63 initial velocity over 2, which is the time. So acceleration is negative 32 meters per second squared. That's our acceleration. Okay, so this acceleration being negative means that of course this jet was reducing its speed. Okay, it means that it was reducing its speed. That's why we have negative 32 meters per second. It was, in other words, decelerating. It was decelerating. That's why it's a negative acceleration. Okay, let's look at part B. Part B is saying if the jet touches down at x subscript I equals 0, what is its final position? What is its final position? Okay, just being given this information, touches down at x subscript I equals 0, means that it touches down at the origin. Okay, so we can choose the origin, touches down at the origin. Okay, if the jet touches down at x subscript I equals 0, what is its final position? So we want the position now. And we know one of the equations for position. Let's see what we have. Okay. Alright, so from what we have, an equation involving position, the simplest one to use is just this one because we also have the time. So I'll use this equation to work out the position. Yes. So we have x final is equal to Vit plus half At squared. We say x final is equal to Vi, of course, is 63. Vi, the initial velocity, is 63 according to the question, time 2 plus half A is minus 32, T 2 squared. T is just 2 seconds, and x final is equal to 62 meters. Alright, so it's traveled a distance of 62 meters before coming to a stop. This jet traveled 62 meters before actually coming to a stop. Alright, let's look at another question here quickly, which is example 2, which involves a car traveling at a constant speed of 45 meters per second, passes a trooper on a motorcycle hidden behind a billboard. 1 second after the speeding car passes the billboard, the trooper sets out from the billboard to catch the car. Okay, so this trooper is setting out from the billboard to catch the car, accelerating at a constant rate of 3 meters per second squared. How long does it take her to overtake the car? So this trooper is is a policewoman who is trying to catch an overspeeding car. So this car is obviously overspeeding at 45 meters per second. Now this trooper is trying to catch it. Now the question is, how long does it take her to overtake the car? Okay. Alright, so solution. Now the only way the trooper will catch up with the car is when it travels the same distance as the car. That's the only way you can catch up with someone. You have to travel the same distance as the other one. You can be both traveling at different speed, but you have to be, the one behind has to be traveling faster, and of course they have to cover the same distance. So we use the concept of distance to solve this question, where we say x car must be equal to x trooper. X car is representing distance covered by car must be equal to distance covered by the trooper. Now after 1 second, the speeding car travels a distance of x subscript 1 second being equal to velocity times time. Okay, velocity times time. Now why is it just velocity times time? It's because for this part I've just used the formula of saying velocity times time, because if I include the plus half at squared, it won't have any effect because the acceleration of the car is 0. Why is the acceleration of this car 0? This car is moving at constant speed, meaning that its acceleration is 0. So this is why I was saying after 1 second, the car covers this distance, which is velocity times time, which is just 45 times 1 second. And this gives 45 meters. Okay, so after 1 second, this car is already ahead of the trooper by 45 meters. The car is ahead of the trooper by 45 meters. Okay, all right. So now in this question, we have to treat the position of the trooper, or the position at which the trooper starts, as the origin. That's how we have to treat it. We have to treat it as the origin, the position of the trooper. We have to treat it as the origin. Okay. Now, for the car to travel the same distance as trooper, okay, we must compensate the 45 meters to the distance traveled by the car. Okay. We want these to travel the same distance, so that's why we're compensating the distance which is already covered by the car. And you see, in this case, we're treating the origin as the point at which the trooper starts. Now by the time the trooper is starting, the car has already covered some distance. Okay, the car has already covered some distance of 45 meters. Okay, so we must compensate the 45 meters to the distance traveled by the car. All right, that is x car, that's x subscript car, must be equal to that 45 meters, which is the missing distance, plus 45 times time. Okay, so this 45 is representing the distance after 1 second. Okay, and this part is representing the unknown distance covered. So this part can even be completed to say 45t, just this part here. If we want, we can complete it to say 45t plus half at squared. But again, as we did for the first part, we said that acceleration of the car is 0. So there's no need to include this part for the half at squared. It's just 45 times time. This is just the vi times time part. So x car is just 45 meters plus 45 meters per second times time. Okay. Now the distance covered by the trooper is just, now remember the trooper started from the origin, okay, and it started from rest. So x trooper will just be velocity times time. Its initial velocity was of course is 0. The trooper was initially at rest, that's why its initial velocity is 0 here. Now 0 times time to just be 0 plus half a t squared. Our a for the trooper is 3 meters per second squared. You see, the trooper is accelerating, that's why for the trooper we're including this part here. So 0 times time plus half a t squared. Now using these two equations, we know that the distance covered by a car is just this part here, and the distance covered by a trooper is this part here. We must make their distances to be equal to each other. So this is why we say x car must be equal to x trooper. So as you can see, the right side of this must be equal to the right side of this, which is 45 plus 45t must be equal to half 3t squared, like that, which is this thing we have here. Simplifying this further and rearranging, we'll have this expression. Now this expression is a quadratic equation which you can solve using the quadratic formula, which we all know the quadratic formula. So using the quadratic formula, we just say negative minus 45 plus or minus square root of minus 45 squared minus 4, 1.5 times negative 45 over 2 times 1.5. So this is just the quadratic formula which is known by everyone. Let me just read it out. The formula which says negative b plus or minus square root of b squared minus 4ac over 2a. The same equation which you are using in grade 12. This is what we're using to solve for this quadratic equation. So using the quadratic formula here, we'll find time equals 30.9 seconds. So it takes 30.9 seconds for the trooper to catch this speeding car. Okay, it takes this much time. Yeah. All right, let's look at another example, which is example 4, where we have a car moving at 30 meters per second, slows uniformly to a speed of 10 meters per second in a time of 5.0 seconds. So this car is moving at 30 meters per second and slowing down uniformly to a speed of 10 meters per second in a time of 5 seconds. Determine the acceleration of the car. Okay, so we have the initial velocity and the final velocity and the time. Once to find the acceleration, we're going to apply this formula, which we also applied in the previous example, I think. We'll just say A is equal to VF minus VI over T. Okay, final velocity minus initial velocity over time. So we've been given moving at this, slow uniformly to a speed of this, which is that minus that over the time, which is 5 seconds. Working out this, will get minus 4.0 meters per second. So this is our acceleration. Part B is just saying the distance it moves in the third second. So the distance it moves in the third second. Wow, this is interesting. So the third second is what we're looking at. So when you look at this question, if you are fast, you may get it wrong. The question is just wants us to find the distance it moves in the third second, not in 3 seconds, but in the third second. Okay, in the third second only, that's what we want. So to get the third second, we must subtract the distance moved in 3 seconds minus the distance moved in 2 seconds. That's how we get the distance covered in the third second. Okay, all right. And the third second is just, of course, the portion of time between 3 seconds and 2 seconds. That is the third second, which is what we're getting here. So distance covered in 3 seconds minus distance covered in 2 seconds. Using the formula for equation of motion, we say 30 times 3 plus half minus 4, which is acceleration, 3 squared minus 32 plus half minus 4. Excuse me, sorry about that. Plus half minus 4, 2 squared. We have something like that. Well, we'll say x is equal to 20 meters. So that's our distance, 20 meters there. We have it. So now that is something which we, yeah, this is good. So we're saying that in the third second, a distance of 20 meters is covered. That's in the third second only. All right. Now we can look at acceleration due to gravity. So acceleration due to gravity is what we're looking at now. The gravitational or free fall. So gravitational is free fall, while we assume that an object is moving in a vacuum. That's free fall. So the gravitational acceleration denoted by the Greek letter g. So this is small g, is vertically downwards directed. So acceleration due to gravity is always directed vertically downwards. That's something you have to note. That's a key point. Is vertically directed downwards acceleration. So this is vertically downwards directed acceleration of a body moving only against the force of gravity. So it only moves against gravity only. The only force that acts on a particle moving vertically downwards freely is gravity. So on the Earth, g is 9.81 meters per second squared. That's gravitational constant, g, which is 9.81 meters per second squared, while the exact amount fluctuates a little depending on location. Okay, so it may differ depending on the location where someone is. The acceleration due to gravity may differ and it may fluctuate. You may find that someone who is on the North Pole of the world may experience a different gravitational force from someone who's on the South Pole, or maybe someone who's on the equator can experience a different gravitational force. It differs depending on the location. For example, someone on the moon may feel a gravitational force which is different, Yeah, and on the moon it's much smaller than on the Earth, like 6 times smaller than on the Earth. So that is gravity. It is always vertically downwards directed with a magnitude of 9.81 meters per second squared. And we can look at an example, which is example 5, where we have a ballast bag dropped from a balloon, right? A ballast bag dropped from a balloon that is 300 meters above the ground and rising at 13 meters per second. So this ballast bag is dropped from a balloon that is 300 meters above the ground, okay, and rising at 13 meters per second. Okay, so you know those air balloons, okay, which is this balloon here, but a ballast bag. Someone in the balloon drops a ballast bag, okay, from this same balloon which is rising at 300 meters above the ground. Okay, so this balloon is 300 meters above the ground and rising at 13 meters per second. So it is rising at this rate of 13 meters per second. Now for the bag, find the maximum height reached. Okay, want to find the maximum height it reaches. Of course, with respect to the ground which is 300 meters below the balloon. So this ground is 300 meters below the balloon. Okay, now for the bag, find the maximum height reached. Okay, so as you can see, this bag is rising, right? Now, I mean, this balloon, of course, is rising at this speed, 13 meters per second. So if you drop it, if you drop the bag will also rise with an initial speed of 13 meters per second before coming instantaneously to rest. Yes, that's what will happen. When you drop this bag, it will rise for a short distance and then it will get to a speed of 0 and then starts falling again downwards. So this is what will happen because when this bag is dropped, it will rise with an initial velocity of 13 meters per second before it reaches the maximum height and then before it starts falling down again. So it will be initially with 13 meters per second because that's the speed at which it was thrown. Okay, so now we're being asked to find the maximum height reached. The maximum height reached by this bag and its position and velocity 5 seconds after it is released and the time at which it hits the ground. So making the starting point as the origin, that's the first assumption we make, and taking up as positive. So in this example, we're taking up as positive, meaning that any vector which points up is positive. Any vector which points up is positive, any vector which points down is negative. And all this is made with reference to the origin we've chosen. Okay, so making the starting point as origin, okay, that's what we're saying. Now let's find the maximum height reached. The maximum height reached by this bag. So now to find the maximum height, and we know that height is measured in the vertical plane or in the vertical axis. That is what we use. That is what we use to find the height, the vertical axis. Now we'll use one of the equations of motion, which will help us to easily find the height, which is v squared is equal to vi squared plus 2ay. Okay, this equation is commonly read as depending on the textbook you're using. In some textbook, you see it written as v squared is equal to u squared plus 2as. It's the same, but this one is more specific because it's also showing the axis in which this bag is moving. So v final in the y squared is equal to v initial in the y squared plus 2 acceleration in the y times y, which is the displacement in the vertical plane. So we want to find y in this case. Okay, now since it is rising, our final velocity will be 0 because it just has to come momentarily at rest because it's being pulled by gravitational acceleration. This bag is being pulled by gravity. It's being pulled by this gravitational acceleration, which is always vertically downwards directed. So gravity is always downwards directed. That's a very key point you have to note. It is always downwards directed. All right. I think that is something which you should keep in mind whenever you're solving problems. Gravity is always vertically downwards directed. So the final velocity at the maximum point or the maximum height, it will just be 0, right? The final velocity will be 0 squared must be equal to viy squared. Viy, initial velocity in the y, is just 13 meters per second because that's the point at which it was dropped, right? That's the initial velocity before it got to 0. Okay, so 13 squared plus 2a. Now a is the acceleration, which is minus 9.8. Why is it minus 9.8? Because it is going downwards. We've chosen up as positive. When we choose up as positive, we mean that every vector which points up will be positive, every vector which points down will be negative. But gravity, we know that it is always vertically downwards directed with this acceleration. This is the acceleration with gravity, which is always vertically downwards. That's why it has a minus 9.81. So you must choose your axis. When you are working out problems, you must choose which orientation is positive and which one is negative. In this case, we've chosen up positive, down negative, and gravity is always downwards. That's why it has a minus 9.8 times y, this y here. So making y the subject of the formula, we're going to have this expression, which is 8.6 meters upwards. So this 8.6 meters represents how much it has risen from the origin. This 8.6 meters is representing how much this balloon has risen from the origin at which it was released with this speed of 13 meters per second. So after it was released with a speed of 13 meters per second, it went upwards with a distance of 8.6 meters. But from the point it was released, this bag or balloon was 300 meters below the ground. So if it has risen by this much, but initially it was also 300 meters below the ground, then we have to add this rise plus how much distance it was below the ground. So we must add 8.6 plus 300 to get the actual height it will have. Hence we'll say the maximum height reached is just this sum, 300 plus 8.6, which is 308.6 meters. Okay, now part B, its position and velocity 5 seconds after it is released. Its position and velocity 5 seconds after it is released. Okay, 5 seconds after it is released, what is its position and velocity? Okay, find the position. Of course, we use one of the equations of uniform motion. 5 seconds after it is released, let's see what we get. So we know we're working with the vertical axis here because this object is dropped vertically. Okay, it is dropped in the vertical axis. That's why we're using y here. Okay, that's why we're using letter y, like the y-axis, the vertical axis. So using y is equal to VIYT plus half AYT squared. We're going to have VIY, of course, is 13 meters per second, that's initial velocity, times time, which is 5, plus half AY, which is minus 9.8, times t, which is just 5 squared. Hence, y is equal to minus 57.5. Okay, y is equal to minus 57.5. So now this is our displacement here, minus 57.5. Now we have a negative value for displacement here. This simply means that it is below the origin. It is 57.5 meters below the origin which we chose, and the origin was just the point at which this bag was released. So it is 57.5 meters below the point at which it was released. That's what this displacement means. It means that it is 57.5 meters below the point at which it was released. Okay, that's what we're saying here. It means 58 meters below starting point. Of course, the starting point is the point at which this balloon was released. Now, if it is this much below that point, this means that For us to get the actual position with respect to the ground now, we want to get the actual position with respect to the ground, we just say 300 meters minus 58 meters, or 58 is just the round off from 57.5. When we round it off, we get 58. So 300 minus 58 is, which is just 242 meters. Okay, so we're saying that it will be 242 meters below the ground. 242 meters below the ground. That is after 5 seconds. Now, the velocity after 5 seconds. We know that Vf is equal to Vi plus Ayt. So Vf is just 13 plus A, acceleration, which is always vertically downwards, minus 9.81 times 5, which is time, and we're getting minus 36 meters per second. Minus 36 meters per second, meaning that it is moving downwards. Okay, because we know that velocity is always a vector. Velocity is a vector, and it has a negative sign here, meaning that it is going downwards. Since we chose up positive, it has a negative value, meaning that this object is going downwards after 5 seconds. So which is this thing I've written, this means it is going downwards with a velocity of 36 meters per second. Simple. Now let's look at part C. Part C is the time at which it hits the ground. The time at which it hits the ground, we just have to take the total displacement covered. We have to use the total displacement. So the starting point is 300 meters below the ground. That's what we know. Now using y is equal to VIYT plus half AYT squared. The total displacement is just negative 300. Okay, negative 300 is equal to 13t plus half a, which is minus 9.8 t squared. Okay, and 4.9 t squared minus 13t is minus 300 is equal to 0. I'm getting this after simplifying this and making everything cross to the left. We're getting this here. Okay, so you simplify this, you get that. And when you get that, this is a quadratic equation. You can solve for time using the quadratic formula, which is this expression when you replace the values in the quadratic formula. When you replace all these coefficients of these variables in the formula, you find that this expression is what we are having. So now from here, we find that t is equal to 9.26 seconds, or t is equal to 6.6 seconds. But a negative time is always invalid time. We don't consider it, and we only consider the positive value of time, which is 9.26 seconds. All right, very good. Very good. Time is always positive, and of course we always chose positive time here. We choose positive time here. Good, 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 good. All right. For now, we'll end here, and we'll continue with these problems in the next video. Thank you very much for joining me, and have a good time.